Okay, welcome everybody to the annual John Bell Day and the John Bell lecture. I want to do two things before Andreas begins his lecture. So the first is to introduce John Bell and his legacy, and the second is to introduce Andreas as our speaker for today. So let me first tell you a little bit about John Bell. John Bell was born in Belfast in 1928. Financial pressure and the need to find work meant that none of his immediate family completed high school. He did, and he went on to study here at Queen's University Belfast and graduate with bachelor degrees in both experimental and mathematical physics. A PhD in nuclear physics and quantum field theory from Birmingham followed. And then after an initial period in Harwell, he took up his position in CERN. And it was this post that allowed for him to develop his groundbreaking insights into quantum mechanics. He died suddenly from a brain hemorrhage in 1990, and poignantly, this was after having been apparently nominated for the Nobel Prize in the same year. John Bell Day is an attempt for us to recognize the immense contribution that John has made to modern physics. Held in November, it aligns with the timing of the submission of the groundbreaking 1964 publication on the Einstein-Podolsky-Rosen paradox that is so intimately linked with Bell's inequalities. This year is the 61st anniversary of the manuscript submission, and to mark the occasion, Professor Andreas Wallraff from ETH Zurich will give his lecture entitled Loophole-free Bell Inequality Violation with Superconducting Circuits. The lecture is particularly timely and exciting, given its link to the 2025 Nobel Prize in Physics. Okay, let me briefly then introduce you to Andreas. He obtained his undergraduate education from RWTH Aachen and also from Imperial College London before taking research on solitons and microwave generation from Josephson vortex oscillators in Jülich. After graduating with his diploma in physics, he joined the University of Erlangen-Nuremberg and continued his interest in vortex dynamics and superconductors. He stayed for a while after his PhD to develop a new effort on quantum information processing before joining the Department of Applied Physics at Yale, working with Robert Schulkopf and Michel Devoret, one of the 2025 Nobel laureates. His work in Yale stimulated a wealth of new research in quantum optics, quantum information processing, and quantum information science. In 2004, Andreas was appointed as an associate research scientist at Yale, and then moved to ETH in 2005. Still at ETH, he now leads a team engaged in research in quantum optics and quantum information processing with superconducting circuits using large bandwidth sensitive microwave techniques at ultra-low temperatures. Andreas, it is genuinely exciting and timely for us to be able to welcome you here and for you to deliver the 2025 John Bell Lecture. Thank you.
Okay, thank you very much. Thank you very much for the kind introduction and also for the invitation to speak on this great occasion. The work of John Bell has certainly influenced the work that we're doing in our own lab. And this will also be the topic of my presentation today. So if you're interested, you can use this QR code here and scan it and download a PDF of the slides to make some notes on them if you want to. So also on the next slide, I'll have that QR code so you can still scan it. So here's the title of the talk again, which you've heard about already, and a list of the current team in my lab at ETH Zurich, which has both researchers in our lab and also a technical team that helps us build exciting and sometimes big experiments that one of which you will see today. So doing this type of research and also working on quantum information science and quantum information processing with superconducting circuits is a major effort. It's being pursued worldwide by many labs in academia and also in industry. And to reach the current state of the art, not only the work and the contributions of our current lab members should be acknowledged, but also those of our previous lab members. So here's a slide that I like to show, both to thank the contributors to research in our lab, but also acknowledge their own big successes in moving on to faculty positions and moving on to industry. sometimes related to quantum information science directly, and sometimes related to industry that provides tools in and around quantum information science. So I'm grateful to all of them and also to our current and past collaborators. So I think most of you are likely no experts on the quantum physics of superconducting circuits. So I'll spend first couple of minutes to introduce the quantum physics of electronic circuits to you. So typically, electronic circuits are built of basic circuit elements such as capacitors, inductors, or resistors. And sometimes, or in modern electronic circuits and integrated circuits, they're also combined with transistors that form all of our standard information processing technology these days. And usually, if you think about these electronic circuits, you don't really think about their quantum physical properties. Though these circuits can behave quantum mechanical, and indeed this insight was awarded the Nobel Prize just this year. And I'll try to give you a little bit of a background of why that is. So maybe I guess most of you have learned a little bit about quantum physics at some stage in their education, and you are reasonably familiar with the quantum physics of microscopic objects, yeah, such as electrons, for example. An example could be an electron bound to a proton forming the hydrogen atom, and you've probably solved the Schrödinger equation for that. Yeah? So microscopic particles, we know that they behave quantum mechanical. So if you look at charges in electrical circuits like individual electrons, yeah, these are microscopic objects, and you could maybe envisage this this scenario that I've depicted here in this graphic of a capacitor. And on this capacitor, if you imagine a single electron, this capacitor could either be on the lower capacitor plate or the upper capacitor plate. And if the electron was a classical object, yeah, it could be only on either one of these two capacitor plates. But indeed, if you believe into the quantum mechanics of microscopic particles, you would also imagine that that electron could maybe be in a superposition of being on both of these capacitor plates simultaneously. And while this is simplified, I do like this kind of pictorial representation of a wave function presenting this coherent superposition of the electron being on the lower capacitor plate and the upper capacitor plate. So you might not be very surprised about that. That is in principle a possibility. What maybe you've thought less about is the fact that there could be a loop of a wire with an inductor formed through which a current could flow. And typically a current is composed of a large number of electrons that can flow either clockwise or counterclockwise through this loop. So quantum mechanically, you could now imagine that the system could be in a superposition of current flowing both counterclockwise and clockwise at the same time. And I can again write down this pictorial wave function representing this situation. So now there's sort of an interesting connection between what you may know of the quantum physics of particles moving in three-dimensional space and the quantum physics of electronic circuits. So when you think about a particle moving in three-dimensional space, yeah, you could write down its total energy in terms of its kinetic energy and the potential energy. You know, for example, the kinetic energy of an electron moving in the potential of the nucleus of the hydrogen atom. And then the total energy could be written down, yeah, as the sum of the kinetic energy and this potential energy of the electron in the field of the hydrogen nucleus. And then if you wonder about the quantum physics of such a system, you take this Hamiltonian or the Hamiltonian function and you replace the position and the momentum, so x and p, in that representation with the position operator and the momentum operator. And then when you have done that, you have a Hamiltonian operator. And this Hamiltonian operator you can then use to solve the Schrödinger equation and learn about the quantum physics of the hydrogen atom, for example. So in electronic circuits, you can write down the total energy of an electronic circuit in terms of the charges on a capacitor, on capacitors in the circuit, and in terms of the magnetic fluxes that are created by currents flowing through these loops. So current flowing through such a loop will create a magnetic field, and together with the surface area of this loop, this defines a magnetic flux. And interestingly, in electronic circuits, these quantities the charge Q and the flux phi are conjugate variables in a similar way that position and momentum are conjugate variables. And as a result, you can now write down the total energy of any electronic circuit, essentially in terms of the charges on capacitive elements and the fluxes generated by currents flowing through the inductive elements. And so the total energy can always be expressed in the charge degree, in the charge conjugate variable and in the flux conjugate variable. And similarly, as you would do it for the hydrogen atom for position and momentum, you can now replace the charge and the flux by their corresponding operators, which then creates a Hamiltonian operator for your electronic circuit. And then you can go ahead and solve Schrödinger's equation for the electronic circuit. And you will find all the things that you maybe know of in terms of the properties of atoms, for example, that energy is quantized, that there can be transitions between the different energy levels during which photons either get absorbed or emitted from an atom, and the same thing can actually happen in electronic circuits. So charge and flux are conjugate variables, and for example, their commutator has certain properties in a way that there is an uncertainty relation between the charge and the flux as it can be measured in these electronic circuits. So then typically we don't only look at sort of individual capacitors or individual inductors, but we combine these circuit elements to more complex circuits. Here's sort of the next more complex step that you could do is you could combine a capacitor and an inductor in parallel with each other. Yeah, and I guess many of you know that this is now a harmonic oscillator, sort of an LC resonator. And the Hamiltonian for that circuit is both quadratic in the magnetic flux that is generated by a current flowing through the inductor, and it's quadratic in the charge Q on this capacitor. And because of this property of being quadratic both in the flux and the charge, which are the two conjugate variables, this describes a harmonic oscillator. And then if you think about how you would quantize this harmonic oscillator, you would find its quantized energy levels. And harmonic oscillators are characterized by this feature that all of their energy levels are exactly equidistant from each other. And so as physicists, we frequently like mechanical models for things, even if this is an electronic circuit. And one of the ways to think about the quantum physics of this electronic circuit is to imagine the dynamics of a particle moving along a coordinate, which in this case is the magnetic flux phi, in some potential that is a quadratic function of phi in the case of this LC oscillator. And in fact, if you think of this particle moving in this potential, and you analyze the physics of this problem, you'll see that the mass of the particle, of the effective particle moving, is related to the capacitance of this capacitor in this LC oscillator. So similarly, one can investigate sort of an interesting situation in which you replace this linear inductor here by a nonlinear inductor. And this nonlinear inductor is a Josephson tunnel junction. So Brian Josephson, during the end of his master's and the beginning of his PhD, he actually thought about the quantum tunneling of Cooper pairs through Josephson tunnel junctions and derived the Josephson equations, and was awarded a Nobel Prize for that as well in 73, if I remember correctly. So interestingly, when a current flows through such a Josephson tunnel junction, the magnetic energy is not quadratic in the flux that is generated by this flowing current, but it's actually cosinusoidal in this flux generated by this flowing current. And so now you could think about this circuit here as the motion of a particle, now not in a quadratic potential as in the harmonic oscillator, but in a cosinusoidal potential. And in this cosinusoidal potential now, the energy levels are non-equidistant from each other. And the reason for that is if you compare it to the harmonic oscillator here, you see that the potential opens up to higher energies, And as it opens up to higher energies, the energy levels get closer to each other. And so now what is interesting about this is now you could address individual transitions in this potential here by irradiating this system, the combination of a Josephson tunnel junction with a capacitor, by microwave frequency radiation that is exactly resonant with just a transition between one state and another. And it's actually these states that are used in superconducting qubits for doing quantum information processing. And they are also the states that we use to demonstrate a loophole-free violation of Bell inequality. So as I mentioned already, the Nobel Prize in Physics this year was awarded to John Clark, Michel Devoret, and John Martinez, for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electrical circuit. So they did this research in the mid-80s, and at that time it was even unclear whether such electrical circuits would display quantum physical properties at all, whether you could observe tunneling or whether you could observe energy level quantization. And people at that time didn't even think too hard about whether you could create superposition states between the lowest energy state in this potential and the first excited state. And so these three gentlemen were then this year awarded the Nobel Prize in Physics for doing really the first pioneering experiments in which energy level quantization and quantum tunneling was observed. And they essentially used the physics of a particle moving in this cosinusoidal potential. And here's a picture from one of their papers, which is also part of this of the citation for the Nobel Prize and the documentation, which you can read about there. And so what they did is they used the system of a Josephson tunnel junction in parallel with a capacitor, and they applied a current source to it. And what this current source does, it takes this cosinusoidal potential and now tilts it by an amount that is proportional to the current that is applied. So the higher the current is that you apply, the larger is this tilt. And here you also see this particle picture that I've mentioned already before. When the tilt is small enough, the particle will remain localized in the minimum of this potential. And then there's this sort of a critical tilt where this minimum in the potential will turn into a saddle point, and the particle will roll down this potential. And then the AC Josephson equation that actually tells you that once this particle rolls down this potential, actually there will be a voltage developed across the Josephson junction, while when the particle remains in this minimum here, there's no voltage across the Josephson junction. It remains in its superconducting state. And this transition from the particle being trapped to the particle being moving can be used to observe the quantum physics of these devices. So when the temperature is high, actually the particle could behave like a classical particle where it jumps across the barrier by thermally activated processes. But when you lower the temperature to close to the absolute zero, then this thermal activation process will be suppressed. And then you will start to be able to observe kind of the energy level quantization in this potential well. And when the well or the barrier that separates the well from the continuum is low enough, the particle can actually tunnel through this barrier and the Josephson tunnel junction can go from a zero voltage state to a finite voltage state. And by analyzing this process carefully, you can actually measure the tunneling, the macroscopic quantum tunneling in these Josephson tunnel junctions. And then if you would apply a microwave frequency that induces resonant transitions between the ground state and the first excited state in this potential, then the tunneling rate will be higher because now the barrier is smaller and you can see tunneling at a larger rate out of this potential well. And for these groundbreaking experiments, the Nobel Prize was given this year. And it's also the basic physics that underlies all the investigation of quantum physics with superconducting electronic circuits. And in our research, we use these electronic circuits for performing fundamental quantum science experiments with superconducting circuits and for looking into applications in quantum information processing. All right, so let's connect this now to the Bell test. So interestingly, also in the scientific discussion of this year's Nobel Prize provided by the Nobel Foundation, this experiment that we've done in our lab on observing loophole-free violations of the Bell inequality was cited as one of the experiments that was enabled by the early works of the three Nobel laureates of this year. And it was also cited because the experiments that I'll be discussing with you now, there are actually experiments in which Bell inequality was violated in a macroscopic quantum system for the first time. Okay, so what are Bell tests about? So Bell tests are both interesting from a foundational perspective, and in the introduction you heard about that already. So there was this conundrum that was uncovered by Einstein, Podolsky, and Rosen that noticed that quantum mechanics seems not to follow the principle of local causality. And that made them think that maybe there's something missing, or that there should be an alternative theory to quantum mechanics that would explain these correlations that can occur when quantum particles are entangled with each other. And sort of the particularly noteworthy scenario that one considers is if you had two quantum mechanical particles that are in an entangled state, and they're at a large distance from each other, and you perform a measurement on these two quantum particles, you will find out that the measurement outcomes between these particles are correlated with each other. And these correlations cannot be explained by classical physics. And initially it was thought that maybe something is missing in quantum physics that would explain these phenomena. And initially it was mostly a sort of a philosophical discussion, which was hard to test experimentally. But then John Bell, as was pointed out before, in 1964, then published this paper where he proposed an actual experimental test that could be done on quantum mechanically entangled particles. And this test is set up in a way that would demonstrate clearly, based on mathematical principles and experimental outcomes, that the correlations that are observed in entangled particles cannot be classical, but have to stem from quantum physics itself and the entanglement property. And so this was in 1964. And that essentially, at that point, this insight started. First, only a very few experiments that were trying to look into violating these Bell's inequalities to kind of touch on the essence of quantum physics. But also at that point, people then started to start thinking about what these Bell inequalities sort of mean in a more general context, and for example, whether there could be any applications of the ability to violate Bell's inequality experimentally. And I'll mention a few of those here. So Bell tests and the non-locality that it probes are important resources, for example, for device-independent quantum information processing. So quantum information processing where you don't need to make any assumptions about the property of the device. And it's a possibility to independently verify quantum devices and networks. It also allows you to realize secure quantum communication through quantum key distribution, for example. And the ability to perform loophole-free Bell tests also allows you to produce certified random bits, for example, for random number generation in keys that you might use for cryptography or in other applications. So there's both this fundamental physics interest in verifying quantum physics in different physical systems by showing that the correlations are due to intrinsic quantum mechanical correlations and cannot be explained by any other phenomena, and by thinking about applications of this capability of looking at non-local correlations between entangled quantum mechanical particles. All right, so many of you have probably heard about this. I'll just briefly remind you of what a Bell test, this protocol that John Bell had proposed in 1964, how that proceeds. So in a Bell test, you typically consider two parties that are frequently called Alice and Bob. And so Alice and Bob are shown here on the right-hand side in my image as two parties that have a superconducting qubit. So here you see the superconducting qubit being made out of this Josephson tunnel junction, which is symbolized by this box with a cross in parallel with the capacitor. And Alice and Bob, in such a scenario, they are at some distance from each other. And that distance could be, in our case, will be several tens of meters. And what Alice and Bob do is they actually entangle their two quantum mechanical systems with each other into a so-called Bell state. So the Bell state is a maximally entangled state between two quantum mechanical objects. So your Bell test starts out with preparing such a Bell state between two distant quantum mechanical objects. And then in the Bell test, you actually choose to measure the two quantum bits or the two quantum mechanical objects independently from each other. So this measurement is represented here on the left-hand side and on the right-hand side as acting on each one of these two quantum mechanical systems. And in this measurement, the experimenter actually randomly selects a measurement basis. And as you know, in quantum physics, the measurement outcomes depend on the measurement basis that is chosen. And you choose measurement basis on Alice's side and Bob's side independently from each other. So here's this pictorial image of what this basis choice could look like. So there's a blue basis for Bob's side and a red set of bases for Alice's side. And Alice and Bob can either choose to measure in this one basis or in this zero basis. And in addition, there's sort of an angle, little theta, that shows sort of the misalignment between these two bases. And at the beginning of a Bell test, you randomly select a measurement basis both at Alice's side and at Bob's side. And the basis choice that you make either chooses the zero basis or the one basis independently at Alice and Bob. And then with that basis choice, you read out the state of the qubit, and you'll find that the qubit is either in its excited state, where the measurement outcome will be 1, or in its ground state, where the measurement outcome will be -1. And then you repeat these three steps a large number of times, yeah, and typically that's at least a few hundred times or a few thousand times. And if your experimental apparatus allows you, you could even repeat this measurement millions or even billions of times. And then you take these measurements, you both take the basis selections A and B and the measurement outcomes X and Y, and you calculate the Bell inequality with those measurement outcomes. And in many experiments, including ours, you actually take a special version of this Bell inequality, which is called the CHSH Bell inequality. And in the CHSH Bell inequality, you calculate this S value here. And the S value is a sum of 4 terms. And the 4 terms are essentially conditioned on the 4 different combinations of basis choices. Or there's both Alice and Bob could choose 0, or Alice and Bob could both choose 1, or 0 and 1, or 1 and 0. So these are the 4 terms here. And then for these basis choices, you take all of the measurement outcomes X and Y, and you average over the product of the measurement outcome X and the measurement outcome Y, given this particular basis choice. And then John Bell's theoretical insight was, if this is a quantum mechanical system where the two objects are in a maximally entangled state, then this Bell inequality can be larger than the value of 2. While when the system is described by a local classical theory, this S value is bounded by 2, so it can never be larger than 2. And therefore, in an experiment where you measure that this particular measurement quantity is larger than 2, you can violate Bell's inequality, you can verify quantum mechanical correlations in a maximally entangled state, and you can refute any alternative interpretations of quantum theory experimentally based on this measurement of the Bell inequality. All right, so this is the Bell test protocol, and there's a few caveats that pertain to it, and these caveats are known as loopholes. So in early experiments, loopholes were not initially considered, and then later when experimentalists try to close these loopholes one by one. And maybe one of the important loopholes is the so-called locality loophole. And in this to close this locality loophole, you try to separate your two parties, the two entangled quantum systems at Alice and Bob, by a distance that is large enough so that during the time that you take to do this measurement for the Bell inequality violation, there's no other physical mechanism that could actually create correlations between Alice and Bob. And so what does that mean? So if there's any physical mechanism that creates interactions between Alice's quantum system and Bob's quantum system, this physical mechanism would be mediated by some force, for example. And this force propagates at a finite speed through space. And that finite speed must be less than the speed of light. And so what you can do is if you separate Alice and Bob by a large enough distance and you finish your experiment quickly, you can assert that no other physical mechanism could have caused the correlations that are measured between Alice and Bob. And so that requires in loophole-free Bell tests to separate the entangled parties over a large distance from each other, which sounds like a major task for superconducting circuits to achieve. Second loophole is the so-called detection loophole. And closing the detection loophole requires to measure each and every Bell pair that you create. In this Bell inequality measurement, as I'd said, you need to repeat the measurement a large number of times. And in many early experiments, the detection of the Bell states of the individual qubit states was inefficient, so that you would maybe only detect a small fraction of the actual Bell pairs created. And when you do that, you could not exclude that maybe the undetected Bell pairs would show different correlations from the ones that you have detected. And then a third loophole that I want to consider is the so-called freedom of choice loophole, or the measurement independence. And this measurement independence loophole can be closed to the best of our knowledge by choosing the measurement bases randomly at Alice and Bob's side. And there's a few caveats to that, which we maybe can discuss in the questions and answers session at the very end. All right, so there's been a progression of Bell test experiments. As I've mentioned, the original proposal was made in 1964. And then relatively soon afterwards, there were first experiments. Yeah? So in 1972, Friedman and Clauser did a first Bell inequality violation experiment. And this was only 8 years after the first proposal. But in this experiment, essentially none of these loopholes were addressed. And then in 1982, Alain Aspect, as part of his PhD, did a few further Bell tests and violated Bell's inequality, now addressing the first loopholes. So all these early experiments relied on these additional assumptions. So the loopholes were essentially not all closed simultaneously. And a nice review of the steps that experimental physicists did take from sort of Bell's original proposal to doing a loophole-free Bell inequality violation is discussed in this nice article by Alain Aspect in the American Physical Society journal Physics. And so essentially late in the 2010s or so, still there were no loophole-free Bell inequality violations in any of the physical systems. So Alain Aspect worked with atoms and photons, as did Friedman and Clauser, and then there were many other experiments with photons generated in parametric down conversion, for example. And now already some time ago, we then thought, okay, good, maybe we had an idea how one could do a loophole-free Bell inequality violation with superconducting circuits that would address all of these loopholes. And so as time goes, sometime after we had started our project already, then there were first loophole-free Bell inequality violations. And so 2015 is now, it's almost another 40 years after the first experiments, or it's another 40 years after the first experiments done. And it's almost 50 years after the first proposal by John Bell to do this particular test. And so at this time, we started to set up an experiment to do this with superconducting circuits. And we did choose to continue our research work beyond that, first because we thought it was an exciting topic. And then second, also because it's the first of the experiments that actually works with macroscopic quantum systems. And it's an essential test to do in a technology that is also used for quantum information processing. And as I've mentioned, it has perspectives in terms of applications, for example, for random number generation or quantum key distribution. Good, and then there was, of course, also a Nobel Prize in physics related to entanglement and Bell tests in 2022 Yeah, and I would have also imagined if John Bell was still alive, there would have been probably a Nobel Prize for the Bell test, including him at a much earlier stage. Good. So what are the requirements for doing a successful loophole Bell test with superconducting circuits? So I've mentioned there's this S value of this Clauser-Horn, Shimoni, and Holt type, which you want to verify can take values larger than 2, thus violating the Bell inequality. And what this requires is both high fidelity entanglement and high quality readout of the state of the superconducting qubits. You also need to realize measurement independence through this random basis choice. And you need to close the detection loophole, which is something that is reasonably simple with superconducting circuits, because for superconducting circuits, very high fidelity readout has been realized essentially in a way that every time you read out a superconducting qubit, you also get a result. And then maybe the most challenging aspect of doing a loophole-free Bell inequality violation with superconducting circuits is closing the locality loophole, because this requires to perform the experiment on a timescale that is faster than light could travel from Alice to Bob before the experiment is finished. And so we estimated how much time a single trial of the Bell test would take. And it's a combination of choosing the basis randomly, of measuring the qubit quickly, and waiting for the signal propagation delays. And when we thought about this experiment, we thought that we would need about 100 nanoseconds to perform this experiment in every trial of the Bell test. And this would require us to separate the two parties, Alice and Bob, by about 30 meters, because at the speed of light, you would take about 100 nanoseconds to travel these 30 meters. And so any physical interaction that would lead to correlations between Alice and Bob would yeah, couldn't play a role in the measurement outcomes if they're done faster than in 100 nanoseconds. Good. And so then we did go ahead and wondered, okay, good. Superconducting qubits typically live in cryostats. Many of you have seen these cryostats. These are the ones that are used for quantum information processing at academic labs and also at companies. And now you need to have qubits and be able to entangle them that live in essentially 2 different cryostats. And the way that we wanted to go about it is to entangle the 2 qubits by having them exchange a single microwave frequency photon. And that makes sense because in quantum devices used for quantum information processing, you actually also create entanglement by having the qubits exchange photons with each other, either sort of virtual photons or real photons. But typically this happens over distances of maybe a few microns or a few millimeters, but we needed to do this now across distances of several tens of meters. And so we've essentially decided that we would build a system in which the 2 cryostats are connected by a long cooled vacuum tube to each other. And the interesting bit is if you have a superconducting waveguide, actually the superconducting waveguide can transfer microwave frequency photons from one qubit to the other with very low loss. And this needs to be a system that is buildable and cools down at a reasonable time, and maybe you want it to be modular if you want to use it for other applications. Okay, so we came up with this concept. A typical cryostat has a vacuum can, a radiation shield at 50 Kelvin, one at 4 Kelvin, one at about 1 Kelvin at the still stage. And then the lowest temperature that these cryostats can reach is typically about 10 millikelvin. And there's another shield, and the qubits live within this shield. And so what we essentially did, we turned one of these cryostats on the side, and having this horizontal vacuum tube, and the horizontal vacuum tube has this same set of radiation shields as the cryostat that house the microwave frequency waveguide that connects one system with the other. And so we did go ahead and build this thing. So here the diameter is maybe about sort of half a meter. You see the radiation shields, and you see a rectangular aluminum waveguide traveling through the center of this arrangement. Okay, here's a picture of one of these modules. And on the next slide, I actually have a little video which gives you a peek into our lab, where you see these 2 cryostats connected to each other through this waveguide. And it's impressive setup. And if whenever you are in Zurich, you should sort of ask us, and we would be happy to give you a tour to take a look at it. So you see this large horizontal tube that runs through our 30-meter long lab. So you see one of the cryostats at one of the ends of the setup. And then with our little drone, we fly back into the other direction. We pass a central cooler, and we see the other cryostat at the other end. Yeah? And so this was a bit of an effort to set up this experiment. Here's a CAD drawing of it, cryostat on the left-hand side, cryostat on the right-hand side, a long horizontal tube. There's about 1.5 tons of copper radiation shields in this setup. It has about 14,000 screws. It all needed to be designed, manufactured, and put together. And you need to be motivated to do it. And the motivation was to do a loophole-free Bell test with these macroscopic quantum systems to essentially perform a litmus test of quantum physics also with superconducting circuits. Okay, maybe for a little bit on the thermodynamics of this. So we set up this cryostat. We have temperature sensors everywhere. And the interesting bit about it is that even 15 meters away from the two dilution refrigerators, which cool this waveguide here in the center, the highest temperature is about 50 millikelvin, so about 50 thousandths of a degree above absolute zero. And this cryostat takes some time to cool down, so it's about 7 days or so. But it works, and if you were to use such a system for some interesting other applications over larger distances, you could probably build systems that are even longer than that. All right, so what are the actual requirements on violating Bell's inequality? So I mentioned the S value needs to be larger than 2, and the actual achievable S value depends both on the degree of entanglement that can be achieved, which we have verified to be large when we did experiments with 2 chips that were only connected by a short piece of microwave cable. And the second thing that is required is that your readout fidelity needs to be large. And the specific combination of the degree of entanglement and the readout fidelity puts a bound on by how much you could violate the Bell's inequality. And in this plot here, you see the different values that the Bell inequality could take in dependence on this entanglement measure, which is known as the concurrence, and the readout fidelity. And when we started this experiment, we had done already preliminary experiments that in which we verified that we could achieve a concurrence that in this plot is about here, and that we could achieve a readout in about 50 nanoseconds that is about here, and that would place us in this region where we were fairly confident that we would be able to violate Bell's inequalities in our experiments as well. Good. So the first step that you need to do in your experiment, you essentially need to entangle a qubit in one of your cryostats with a qubit in the other cryostat. And this is done in our experiment by sending a single microwave photon from one of the qubits through this cooled waveguide to the other qubit. And that in itself was a nice piece of physics. The protocol was based on a suggestion from Ignacio Cirac. And our experiment was the first one that actually deterministically used this single photon exchange to entangle any type of remote qubits with each other. And this type of approach is also generally interesting to entangle qubits in quantum computing hardware infrastructures. So here's a picture of what such a device looks like. So the object of interest is like the integrated superconducting circuit looks like. Here in the center, there's a superconducting qubit. The red part is the capacitor. The 2 Josephson tunnel junctions are in this lower part of the structure here forming the qubit. And then there's some piece of circuitry which you can use to actually emit a photon to the right. And then there's another piece of circuitry that allows for a fast 50 nanosecond short readout of the qubit state on the left. And so then you essentially take a second chip of the same type and you house it in the other cryostat. and you connect the two yellow ports with each other. And through these two yellow ports, you can entangle these remote qubits with each other. So here's a picture of what the chip looks like. It sits in a sample package, and this is kind of reflective of the size of the sample package. It doesn't quite reflect the price of it. So then you first go for preparing the entangled state to start your bell test. So it's a resource in your bell test for your bell test. And we've developed this protocol, which I've just briefly alluded to, and it's discussed in this paper by Philip Corpius from some time ago. So we create this bell state that I've mentioned to you before, and we can characterize its properties by measuring the density matrix of this bell state. And when we do that, we can determine the fidelity, which is reflective of the quality of that bell state, and was about 80% in this particular experiment. And the main source for infidelity is finite loss of the photon when it propagates from the qubit in one of its sample packages to the qubit in the remote cryostat in its own sample package. Good. So how is this? This entanglement is essentially generated in a multi-step process. So first, at Alice's side, you excite the qubit in its excited state. Then you bring it into a superposition with its second excited state. You apply a pulse that entangles the qubit itself with a propagating photon. And then at the remote end, at Bob's side, you essentially apply an inverse pulse, which absorbs this photon and then maps the qubit photon entanglement to a qubit entanglement. And that creates the entangled state that your bell test is working with. Then the actual bell test, the moment at which the time gets started for verifying that your bell test is actually loophole-free, starts with randomly selecting a basis. And for this random basis choice, we actually use a physical random number generator that also has been used in other loophole-free bell tests that is described in this publication here. So initially, we choose independently the measurement basis at Alice and Bob's side, and that sort of starts the counter, and that also starts these kind of light cones or so. And the light cone of Bob's side will intersect the qubit at Alice's side at some finite time, yeah. And you want to have your measurement be finished before the light cone intersects the location of the remote qubit. So we choose the bases A and B, and the basis rotation actually gets implemented by applying a short microwave pulse to the qubit. So there's some finite amount of time for choosing the basis in the hardware. Then this basis choice triggers a microwave pulse that needs to propagate towards the qubit. And the microwave pulse has a finite length, which then rotates the qubit given the basis that was chosen. And then essentially already the final step of this bell test is to read out the qubit state. And this readout takes about 50 nanoseconds. And actually it was quite a bit of work to get the readout as fast as this. It's for many, many years, it was actually the record-breaking speed and fidelity combination in superconducting circuits. And it really enabled this loophole-free bell test. And it also enabled later high-quality quantum error correction protocols in our labs and elsewhere. And the specifics of the readout process is discussed in this paper here by Theo Walter. So the readout signal itself is on for about 50 nanoseconds, and the readout signal then has to propagate towards our detection electronics, and there it's recorded. And now the total time here is targeted to be less than the threshold time that light takes to propagate from one of our qubits to the other. And with this, at this time, we then determine the state of the qubit, both at Alice's side and Bob's side. And if the qubit is in the ground state, we assign one value. And if it's in excited state, we assign the opposite value. And these are the input values for this Bell inequality evaluation. So here's again a reminder for this Bell test protocol. You've seen it before. We essentially have these basis choices A and B, and we multiply the individual measurement outcomes at Alice with the individual measurement outcomes at Bob and calculate the average, and then determine this S value. So these are the experimental results of the experiment published in this paper here. And so in this first plot, what is plotted is the four individual terms in this Clauser-Horn-Shimoni S-value equation plotted individually versus the angle theta between the two basis choices. I mentioned in the beginning that there's an extra degree of freedom, which is the angle between the two bases, which you can choose. And in typical Bell test experiments, that angle is actually varied, and the Bell violation is achieved at a subset of these angles. And so the individual terms here oscillate sinusoidally with this value. And then if you have the terms available, you can also go ahead and calculate the actual S value in this CHSH version. And you see that also that S value oscillates. And the important part is that this S value now crosses this boundary of 2, which essentially distinguishes the potentially classically explainable realm from the one that can only be explained by quantum physics. And so what we observe in these areas here is that there is a Bell inequality violation because S is larger than 2. And you can kind of simulate it given the quality of the different entanglement generation and measurement protocols and find good agreement. So you see that it violates Bell inequality by some amount. So you would want to look closer. So we've looked closer in the regions where the Bell inequality is violated by taking a few more angles and averaging a bit more in this region. And now when having zoomed in, you clearly see that there is a region where S is either larger than 2 or smaller than -2 by a significant amount. And there's different ways how to analyze whether this violation is statistically significant or not. For example, one thing that you can do is you can calculate the standard deviation of the measured S value and determine its value. And the standard deviation is shown here. So in this case, we have done about 1 million Bell inequality violations in this experiment. And therefore, the statistical uncertainty is small. So this S value violates this bound of 2 by 22 standard deviations. And I think any particle physicist would be happy with such a result. What you can also do is you can calculate a p-value that estimates the probability of your outcome being contradicting the hypothesis that you made initially, namely that the Bell inequality is violated. And a contradiction here would have a tiny probability that is mentioned here. Good, and so this was our Bell inequality violation with superconducting circuits. And I'll finally address in 2 more slides the loopholes in this case, and I'll also sort of give a short outlook. So the freedom of choice loophole was addressed by using physical random number generators. The detection loophole was closed by taking all the measurement outcomes into account, which is possible in superconducting circuits because of the high fidelity readout that measures every prepared pair. We've closed the locality loophole by placing the qubits in 2 distant cryostats. And this locality loophole needed a bit more attention. So then you need to actually determine the distance between the qubits and the relevant components in the measurement electronics. And that turned out to be a bit more than 32 meters, which gives us a time budget of roughly 110 nanoseconds. And then you can calculate the time that the actual experiment took. And we find that the actual experiment took about 107 nanoseconds. So there's a 2 nanosecond margin. And if you look at the statistical errors there and the systematic ones, you see that the locality loophole is sort of closed with about an 8 sigma standard deviation. Good, so this was a special experiment because it's the first one with superconducting qubits that has violated Bell's inequality, closing all loopholes. But it's also interesting because it's quite different from other experiments that have been done before. So there were many experiments with polarization encoded photons from parametric down conversion. And those experiments can generate entangled pairs and violate Bell's inequality at a large rate. Yeah? So at several hundreds of kilohertz. And they violate the the Bell inequality by a certain amount. So here's the violation. So the S value -2 is plotted, and the maximum value is here somewhere where 2 squared of 2 minus 2 lies. So this will have a value of 0.828. And so the loophole-free Bell tests with photons are in this range. They typically have a tiny violation, yeah, but a large rate. And then there's another set of experiments that use either NV center or neutral atoms, and they typically have a much larger violation, but a much lower rate. And sort of the interesting bit about superconducting circuits is that you now have a system in which you can have a large violation and a large rate. And that is interesting because it then makes the system attractive for applications. And these applications I've mentioned already in the beginning, and we've looked at some of them. So for example, we've done a device-independent self-testing experiment that is already published. And we've also done a randomness amplification experiment that is currently under evaluation at a journal. So also what one can say is that in this superconducting circuit setting, it's very likely that we can actually approach an even larger violation and approach its maximum value of 2 squared of 2 minus 2 by improving the fidelity of the entangled state that we create initially. All right, so with that, I would like to conclude and offer some perspectives. So we've demonstrated these basic building blocks for networked quantum systems. So there's qubits at the left and at the right-hand side. These types of systems could be interesting not only for fundamental physics or experiments relating to non-locality, but it could also be interesting in the context of networking quantum computers to each other. Maybe you wouldn't want to do this over 30 meters directly, but you could also have many cryostats sitting next to each other that could entangle their qubits by exchanging photons between them. So then, of course, you could do experiments that make use of this non-locality and demonstrate device-independent algorithms or explore other non-local physics. And it's also interesting because you could investigate quantum electrodynamics in these kind of waveguide settings where the waveguide is very, very long and has interesting properties. All right, with that, I'd like to thank our team at ETH. So that's a picture that we've taken a couple of weeks ago this fall with all our project students as well. And I'd like to thank you for your attention and also point out that we are, of course, always interested in working with talented students and staff. So if you're interested, just drop me an email. So thank you very much.
Oh, thank you, Andreas. That was a stunning talk, stunning in every direction. Okay, so a couple of things. So the first thing is that I was very rude and didn't introduce myself. My name is Marty Gregg. I'm the head of school in the School of Maths and Physics here at Queen's. I am in the Center for Quantum Technologies and Materials, or Quantum Materials and Technologies. But that doesn't mean I'm a quantum physicist, and everybody knows that. But we do have quantum activity here in the school, and that's why we felt very strongly that we wanted to keep the memory of John Bell and his legacy as a high-profile event in Belfast. My only connection to John Bell is that my grandfather's youngest brother was in the same year as him studying physics here at Queen's, and used to tell me stories about how John Bell seemingly didn't even have to listen to the lectures because he would always play chess at the back of the class. Remarkable, really. So I would encourage anyone who has questions that have come up from the talk to put them into the chat. I'll relay them to Andreas. I have a number of questions that were posted before the talk, but they are a little more general in nature. And so, now that we've seen what Andreas has presented, perhaps there'll be more specific questions associated with the really large piece of work that he's just described. So please put those into the chat and I will relay them. I'll get the ball rolling. I don't under. I mean, this is not my field, Andreas. So forgive me. Um, but it struck me that there was probably an interesting detail in how in how and when you hit the starter clock before the speed of light is going to beat you to your measurement. So, if you're using the photon exchange to create the entangled state in the first place, that's going to be an interaction at the speed of light. So you can't start the clock at the point at which you start to cause the entanglement. So how do you know when to set that starter clock to give your results meaning?
Yeah, indeed, the way how to think about it is that the entanglement creation is actually a resource to the bell test. Yeah. So the time it takes for creating this entanglement doesn't matter in this experiment. It could be pre-existing. Yeah? If somebody handed you magically entangled pairs or so, you could do bell tests by just measuring properties of these entangled pairs. So your entanglement generation normally could take as long as you like. Yeah? But the clock starts ticking at the moment where you decide in what measurement basis you want to extract the state of the qubit. And this relates to this random basis choice. And you could ask yourself, okay, how does the random basis choice come about? Yeah, and the state of the art thing to do is to use a physical random number generator that um, which you have verified to produce a good quality randomness to set off the clock at the moment that the physical process in this random number generator that creates its random output starts. And what we use is actually this an instrument provided by the company QSight, which is a spin-off of ICFO in Spain. And this random number generator uses sort of a phase diffusion process in a laser diode or so, of which they could verify that it's a good source of randomness. And this phase diffusion process, when it's finalized, creates a trigger event, which we actually then use to send or not send a short microwave pulse to our qubit that then rotates the basis or not. And the moment where this randomness generation process start, that sets the
That's the clock.
clock the
Yeah.
clock ticking. Yeah, and that's part of this argument that Bell made is that it's the random basis choice. So there's this caveat that sometimes comes up in this context. Of course, if you think everything in the world is predetermined, or there's no such thing as free choice, or we're all living in a big simulation or so, yeah, then you could say, okay, good, maybe someone else knows about what the outcome of your random number generator should be, yeah, and that sort of undermines then this argument. And then this freedom of choice loophole is one of the harder ones to close because you could, in principle, you could argue it away. And there was an interesting experiment that we were also involved in as a warm-up at an earlier stage, namely where these measurement bases were chosen by people. So together with people at ICFO in Spain, we created a computer game that had people create random numbers, and these random numbers were then used in these Bell test experiments to violate Bell's inequalities or these random choices. Of course, because humans choose things slowly, yeah, then you would need to have very, very far separated qubits to actually have with human choices um, um, to create a Bell inequality violation based on human choices.
Beautiful.
So that's an interesting question. And maybe the other question at the other end that you could ask, I don't know whether you were thinking about it already, is like when is the measurement really finished? Yeah, that's the other end. And there's actually also quite a bit of different choices that get made when the measurement is finished. Like, for example, if you wanted to do the most difficult thing, you could say, okay, the measurement is really only finished when some human looked at the result. So your computer analyzes something and it shows you, oh, my qubit was in a ground state or in the excited state. and then all the computer would need to do its work. You need to look at it and then recognize it, and that would probably take you milliseconds or so, in which case this would also extend the duration of the experiment. So typically, what we've done in our experiment, so there's a physical mechanism that performs the readout. And you could ask yourself, when is this physical mechanism concluded? And our readout mechanism is an interaction between the readout measurement tone, which is a microwave frequency tone, and the qubit. And so you could identify the measurement to be finished when this readout tone has fully interacted with the qubit. But what we did is actually we actually waited for that signal to propagate towards our detection electronics and being digitized in the ADC that provides the data to our field programmable gate array electronics that then actually determines that thresholds the signal and determines the state. And if you look at other loophole-free Bell inequality violations, you can actually look at what choices they have made and what variation of or like both on the start side. I think the other loophole-free Bell inequality violations, they use the same random number generator as we did, so they're all on the same basis. But where they determined the measurement to be finished, had some experiments made our choice, and there were other experiments, for example, the one in Delft, the two ENVI centers that they used, they were separated by a kilometer or so. So they had a bit more time to write their data to their hard disk, or at least somewhere in memory, I think. And the supplementary material of this Nature paper that we've discussed this in, it has tables which describes the different choices that were made in the different experiments. And it also discusses kind of the standard deviations by which the violations were made. And here you see that you might say, okay, 8 sigma is starting to be maybe a bit tight, 2 nanoseconds out of 109 or so. But at this level, you can perform this measurement. And if you look at other Bell inequality violations, they're sort of at a similar level.
Perfect. So we have some questions that have come in. Alan McMurray is going to ask a live question. So Alan, go ahead.
Yeah, thanks very much. It was really interesting presentation, really fascinating. My name's Alan, as you worked out. I'm from CCEA, the Council for Qualifications in Northern Ireland, so I would be responsible for the physics part of that. It's been a while, obviously, since I've been involved in the physics at this level, but I found the whole thing absolutely fascinating. I'm very aware of the importance of John Bell and the contribution that he has made to Northern Ireland and indeed to physics in general. And I recognise we'll have a student accommodation now for John Bell. So I think his contribution has been amazing, somewhat undervalued perhaps in terms of what people would know about him, especially locally. In terms of your research, absolutely fascinating. I learned quite a bit there, and talking about the applications of how, these inequalities apply to some of the things you're talking about in quantum computing. And I'm not really in a position to ask more detailed questions, but even to put the apparatus and stuff together to get the results you're looking for, I can only imagine the level of time, work, and patience that you put into that. Absolutely fascinating presentation. Really enjoyed it. Thank you.
Excellent.
That's great to hear.
So we have another question on the chat from Maria, who says, "Thank you for the talk. The question is for her: what is a randomness amplification experiment that you mentioned your team doing?"
Okay, good. So if you have, for example, if you have a random string of numbers that someone has provided to you, and you can analyze its statistical level of randomness, yeah. And if you wanted to improve it, there's even a sort of a mathematical theorem that states that you can't improve the randomness in any algorithmic way, because you use an algorithm that is that works with your input random numbers, and the output random numbers can't get more random in that process. And so interestingly, there is a set of different protocols, and one of which is randomness amplification, where you can actually use the output of such a random number generator, like the one that we use in our Bell test at the input, and the measurement outcomes of a Bell test, and use these two sets of numbers to provably increase the randomness in your string of random bits, and also put thresholds on what any adversary might know about your random numbers. So you can get certified randomness, for example, and say if you're sort of at a national security agency of whatever sort that provides random bits for encryption, for example, yeah, you want to make sure that you would provide the best possible random bits. And there's algorithms that are based on loophole-free Bell inequality violations that would give a physically argued for improved quality of the random numbers that you would use for in such a setting. And we've done an experiment in this direction, and it's like one of the theorists that work on that are from the group of Renato Renner at ETH Zurich, and we've collaborated with them on that. And we hope that that this will be interesting for people to read about.
Yeah, very interesting. Okay, I have another question here from Aditya. Hi, nice talk, Andreas. By Andreas. He explained about entanglement via single microwave photon. I'd like to know how these single microwave photons are generated in the first place, and can this process of entanglement via microwave photons be scaled to a large number of qubits that are each spatially separated?
Yeah, that's also a good question, and I've indeed not said anything about it, or at least not much. So how it works. So our qubits are essentially like any emitter. So when they're in an excited state, they can decay to the ground state by emitting a photon. And in our experiment, we do this in a very controlled way. So usually, if you just excite the two-level system, it will just essentially exponentially decay with an exponential distribution decay to its ground state, like in nuclear physics or in radioactivity or so. So that's not what you want to turn this deterministic, but you want to make it decay in a specific way. And I think I'd shown that already, that one of the things that you want is sort of a time reversal symmetric photon to be exchanged between the two sides. And the way we do that is we actually excite the qubit not to its first, but to its second excited state. And then the qubit itself is coupled to a second resonator. So here's the qubit is represented as an atom with three levels. There's the vertical resonator, is the one that we use for reading out the qubit. The horizontal one is the one that we use for emitting the photon. So we actually drive a transition between this F state with no photon in the resonator and the qubit being in the ground state G with one photon in the resonator. So we essentially map the qubit excitation into a photon in this yellow resonator. And this yellow resonator is then strongly coupled to this waveguide, and a photon just emerges into this waveguide. And if it's time reversal symmetric, so the important aspect of that is that you can then essentially reverse this pulse sequence. So here a photon arrives at the right setup. So the qubit on the right setup is in the ground state, but the photon enters the resonator, and then you can drive this transition here and excite the qubit to its second excited state when this photon arrives. And you can essentially use this in a deterministic way to entangle qubits with each other. And so the interesting bit is that there was this proposal by Ignacio Cirac in 1997, which suggested to do this in a deterministic way. And many physical systems, like in atoms and vCenters and elsewhere, this was tried, but our experiment here was the first one. So if you want to read about the details, you could look at this paper here to really operate in a deterministic fashion. And indeed, you could now ask yourself, okay, could this be interesting in a quantum computing setting? Could you, for example, instead of having one qubit on the one side, another qubit on the other side, could there be tens or hundreds of qubits that use this channel to exchange quantum states with each other to create entanglement or perform some calculation. And indeed, this would be possible. And it's now being investigated as part of extending the capabilities of large quantum computing systems by creating connections between different chips. And maybe on a chip, you would have a set of qubits, and maybe at the edge of the chip, some of these qubits could communicate to another set of qubits at the other edge of a remote chip. And then the interactions could be mediated by a photon exchange. But there's also a few other options how you could do that. But generally, the answer is yes, this could be done.
Excellent. So another question on the chat from Thomas Herteman. And I think this is a nice one. So he's sort of opening up the possibility for more loopholes. So he says, the random numbers are generated by quantum mechanical effects, as I understand, and this is used to verify another quantum mechanical effect. Is this logically problematic? Could there be a hidden interaction between the random number generator and the effect you want to measure?
Yeah. Yeah, indeed. Yeah. So this is kind of a caveat that I've pointed out, and the caveat that I've pointed out already was the worst one that you could possibly imagine. Yeah, that everything is sort of predetermined in some way that you don't even have access to. Yeah? And so this you essentially can't exclude, and you try to be like in any physics experiment, you're trying to understand it as well as you can. You're trying to understand the hardware that creates the randomness as well as you can, and exclude such effects. Yeah. And this is this. So, for example, there was a whole set of papers discussing the workings of this random number generators, and investigating physical random number generators is indeed a whole other research area. And so since I don't know whether that's then totally satisfactory or so, we did the thing that all the other loophole-free Bell test experiments also did, and quite a bit of work did go into this direction in verifying this random number generator. But on the fundamental end, yeah, you can't really fully close this freedom of choice loophole, yeah, because there's no experimental way how you could exclude this predeterminism aspect, yeah. And I said that there were already these efforts, and there was also a paper about that, to use sort of human choices. And the reason for why using human choices was that you would, if you believe that there's free will in humans, or yeah, then you could make sure that the human in making their choices are not predetermined by something else. But indeed, it points at a valid point. And our experiment, in some sense, has nothing to say in addition to that. So it's more like a fundamental problem that all these experiments share.
Very good. So I have progressively less focused technical questions, but I also want to ask you a general question near the end. So Gleb Grabakin from Queens is asking, where is the boundary between quantum and classical, in your view?
Yeah, that's a very good question. There's also, I mean, to like this year's Nobel Prize was given for macroscopic quantum phenomena. This is also very important because sort of like if you look at the media discussions of this year's Nobel Prize, they frequently they kind of stop at the microscopic quantum tunneling, because that's already weird enough. But this is like one step weirder because it's about some macroscopic degree of freedom. And the macroscopicity comes about, and I've mentioned it in the beginning. So there's this coordinate phi or so, which is the magnetic flux, and this coordinate phi kind of is the coordinate one along which you observe tunneling, for example, or which is the coordinate in which defines the properties of your wave functions. Yeah, and some way to look at it is that it's kind of sometimes in solid state physics, people would call this an order parameter also. And this order parameter shows quantum physical phenomena, but the order parameter also governs the motion or the properties of charges and currents in these electronic circuits. So it determines how charges redistribute and how currents flow, and for macroscopic numbers of charges. And so there was a time where macroscopicity was discussed, yeah, and there's also other types of experiments, for example, like a double slit experiment is a classical one, and you would do it like it was initially done, maybe with individual photons, with individual electrons, and then you can think about, could you take bigger things, atoms or molecules or large molecules or maybe even biological objects, and people try to push the boundary. And what it comes down to is always sort of a balance between um, gaining control over the system that you want to observe the quantum mechanics of and its coupling to the environment, so decoherence phenomena. And to some degree, like if you like a quantum computer in the end is sort of a macroscopic quantum thing, or it's like it has you're trying to control the quantum state of this large ensemble of quantum bits, yeah? And you could ask, is there a boundary? Does nature stop you at some stage? And I think the current understanding is that that there's no fundamental level at which nature would stop you, but that it only reflects on your ability to control the system and decouple it from everything that you think gets in the way. And this might, depending on what object that is, yeah, it might be easier or harder to achieve this goal. And people are pushing the boundaries, and indeed, like sort of in the early days of quantum computing, and I also asked myself this question when I think my first quantum computing conference that I attended or so was probably in 97 or 98. And at that time, I still wondered whether somebody will come up with a physics reason why this will all not work. Um, for example, because okay, you're trying to create these macroscopic quantum things, and should there be some physical phenomena that would prevent their workings? Yeah, for example, if maybe I don't know if gravity would lead to decoherence, for example, or a thing like that, and there's proposals for that, and it's trying to be tested. Um, yeah, so I don't think that there's a well-defined sort of a fundamental threshold. It's sort of in some sense it's all practical. And in this, for example, in the early discussions around the experimental or in the early theory work around this year's Nobel Prize, there was work done by Tony Leggett, for example, who tried to make models in understanding how the quantum degree of freedom couples to everything in its environment. Yeah? And the improved understanding of that helped to understand which aspects of the coupling of the quantum degree of freedom to the environment would maybe affect decoherence in the system. And then once this was understood, one was able to essentially try to suppress or switch off these channels through which the system couples to the environment.
Fantastic. So I wanted to ask you. You mentioned it a little bit there in your answer to the last question. This has been apparently from what I can see a very long journey for you in the sense that you said you got the advanced grant to start this kind of work in 2012. Is that right? So, you know, when you're doing this kind of work that requires such, before you get to the physics, you've got this huge, well-controlled laboratory to set up. I mean, it's like a miniature CERN or something. There's so much confidence that has to be injected at the start of the endeavor, that you must have had doubts that you might never get there. So the question is, did you? And how do you deal with that when you're taking on science that's going to mean decades potentially of work before you get the result?
Yeah, so that's a good question. So I think we proposed this project. And I mentioned the reason, yeah. So I think we looked at it. There was this proposal or the theory by John Bell in 64, and then first experiments in 72, and better experiments in 84. And then it was kind of I started to my first qubits I operated maybe in 2004 roughly myself, yeah, and then even in 2010 or 12 there was still no loophole-free bell test, and I thought like, okay, now it's 50 years and these guys have been working, and there's like a whole groups of people who have been working on this for a long time to sort of successively close all these loopholes. And if you look into literature, in particular with photons, then essentially every single loophole was closed individually and then in the various combinations, but none had addressed really all of these aspects. And I thought about maybe writing up one of these ERC grants and what to look at. And then I thought, oh, this is still not done, and I think I know how to do it. And I had a good sense of that it should be possible. But there's always many different ways how you could fail at it. Yeah. And this I've seen sort of maybe different times in my career, like afterwards when you look at it and ask yourself, okay, what else could have gone wrong? There are so many things that could have gone wrong and maybe never make you reach the goal. And if you're determined and really want to do it also on these long scales and really take care of all the details, then you can make these complicated things work. And I think all the quantum computing effort is all in this direction. It's not gonna randomly work or so. You don't just give it a try. You need to be very systematic from all the little bits. And then when you put all the little bits together and you still understand it, and you can move forward and make your big experiment work. And there were a few interesting failures around this experiment as well. Yeah, some that came from maybe a lack of care or maybe missing out on a specific aspect, but then kind of sticking to it and having an ambition to make it work was important. And indeed, for us, it was a 10-year project more or less to get it across the finish line. And I had been a bit more optimistic in the beginning, and then it was a bit of a downer that then the other loophole-free bell tests crossed the finish line before us. Yeah, but they've also been thinking about it for much longer. So.
Well, it's been an absolute inspiration, Andreas. We're coming to the end of our time. So probably I should thank you for a great talk and a great discussion, and thank everybody who has been listening for giving us such stimulating questions and topics for discussion. So let me close this session. Thank you very much.
Thank you.